When the Large Hadron Collider and its massive detectors become operational in 2007, one of its primary tasks will be to look for the Higgs boson. Although formulated by several theorists, it takes its name from one of its proponents, Professor Peter Higgs of Edinburgh University, who today leads a quiet life in an old area of Edinburgh known as Newtown. As he walks each day near his home, this leading field theorist passes the house of a revered predecessor.
This house we're standing outside is the birthplace of James Clerk Maxwell. It's a reminder to me of the way field theory began in the 19th century.
As a pupil of Cotton School in Bristol, he excelled in mathematics. And then he became aware of a famous old boy of the school, the theoretical physicist Paul Dirac.
The name Paul Dirac appeared rather frequently in the school honours board at the back of the platform in the assembly hall. So I got curious about what Paul Dirac did. It very soon became evident when I was a physics undergraduate that I was not going to be an experimental physicist. I was terrible as an experimentalist. At King's College London, where I was an undergraduate, they'd introduced a theoretical option. So I gladly took that.
And it was as a theoretical physicist that Peter Higgs encountered theories by the Japanese-American physicist Yoshiro Nambu that seemed to point the way to understanding particle masses.
In the version of this type of theory which I formulated in 1964, which brought in fields like Maxwell's electromagnetism, fields of this type, in addition to giving mass to the fermions, the quanta of the electromagnetic type of field acquired mass too. This is what has been given the name the Higgs mechanism, though it was actually written down a little earlier by Brout and Onglair in Brussels. And the generation of mass there is the same kind of thing as in Nambu's papers, but it is now working for particles of spin 1, which are the quanta of the electromagnetic type of field. They change from being particles which travel with the velocity of light to particles which travel with anything less than the velocity of light, and that's the massiveness.
Much of these new ideas centre on the rethinking of the nature of a vacuum.
When you look at the vacuum in a quantum theory of fields, it isn't exactly nothing. The vacuum state is the state of lowest possible energy. And again, as in the original classical idea, it's what you have left when you pump everything you can out of your system. Now, everything you can pump out is all the particles, but you don't necessarily get rid of everything. There can be residual fields which remain as a background in this vacuum. So the vacuum is no longer quite as empty as it used to be.
It's the interaction between this field, now known as the Higgs field, and particles that's at the centre of his thinking.
The relation to particles is that in these theories, this background could be deformable. It could be excited by interaction with other things. The excitations take the form classically of travelling waves and so on. But this is quantum mechanics, not classical mechanics. Every time you have travelling waves, the energy and momentum come in lumps.
And in the case of the Higgs field, these lumps are the Higgs bosons that the LHC is preparing to look for. What's intriguing about these Higgs bosons and their source field is that they appear to confer mass on particles.
The way that the background field generates mass is rather like the way in which when light passes through a transparent medium like glass or water, it gets slowed down. It no longer travels with the fundamental velocity of light, c. And that's the way to think of the generation of mass, because in a quantum field theory, all the other particles are also excitations of various kinds of fields, which you can describe by classical waves. Now, these waves travel through this background field, and the way they travel in terms of the relation between frequency and wavelength is altered by the background field, or may be altered. If they interact with the background field, it alters the so-called dispersion relation between frequency and wavelength. Now, when it comes to the particles, which are the associated with those other fields, you take the frequency multiplied by Planck's constant, you take the inverse of the wavelength multiplied by Planck's constant. The one gives you the energy of a particle, the other gives you the momentum of a particle. And so altering the frequency wavelength relation of the waves propagating through the Higgs field alters the energy momentum relation for the particles, and therefore alters the mass.
The problem is explaining the considerable variation of mass between different particles.
In theories of this type, most of that variation is attributed to variation in the strength of the interaction of the particles with the Higgs field. Now, that's not really any explanation. It's simply saying there is a connection between the mass that the particle has and the extent to which it interacts with the Higgs field.
The LHC's detectors will look for hard evidence that it is these interactions with the Higgs field carried by Higgs bosons that are responsible for mass.
As a theoretician, of course, I find the mathematical structure of this kind of theory very satisfying. But on the other hand, if it's not verified experimentally, it's just a game. It has to be put to the test. At the present time, the interesting thing is that the electroweak theory of Glashow, Weinberg and Salam, which was the successful application of these ideas, has been rather thoroughly tested quantitatively for most of the relationships that are built into it in the course particularly of the running of LEP. Now, given that that has been done, it would be rather surprising to me if the underlying idea was not right.
If the Higgs boson exists, the LHC will have the power to detect it. That's assuming the theory is correct.
The theory fits the data in a crude way to about 10% accuracy if you just do what's almost a back-of-the-envelope calculation from the original equations. But then you have to do corrections to this first approximation. And into the corrections, the so-called one-loop corrections, come the masses of all the particles that are in the theory that maybe you haven't yet discovered. Now, during the running of LEP, they pinned down the masses of everything, I think, except the top quark. In 1995, Fermilab found the top quark and produced an approximate mass for it, and that enabled people to look at this correction formula and say, okay, what's left to fill the gap between theory and experiment? That's the Higgs boson contribution. Therefore, the Higgs boson mass should be in a certain range. In 1995, the prediction was a rather interesting one. It was that the most likely values were within reach of LEP, around about energy 95 or 90 or so GeV, and LEP went up beyond that. LEP went up to 114 and didn't find anything. And this was maybe a bit worrying because they were beginning to get to the tail of the statistical distribution. But in the last few months, new measurements reported by Fermilab have revised the mass of the top quark and that favoured value, the most likely value for the Higgs boson mass, is about 117. Now that's tantalizingly close to what the people at LEP thought they might have found. It would certainly be very puzzling for me to think of a situation where somebody could really rule out the existence of the Higgs boson, because there it is. There it is. The theory and the experiment are working very well together in all other respects. So where do you go from there?